Hello everyone. In this module, we can discuss the concept of quadrature phase shift keying. In the earlier modules, we have completed the binary phase shift keying. In this binary phase shift keying, we know that only one bit is grouped per symbol. So that's why the number of phase changes in binary phase shift keying is 2 power 1 because it has only one bit per symbol. So you will have two phase changes. We discussed the two phase changes as 0 and pi. Coming to the quadrature phase shift keying, here we will group two bits per symbol. So because n is 2, the number of phase changes will be 4, which is represented by a letter capital M. That's why in a quadrature PSK, which is also called as 4-array PSK, so number of phase changes is 4. Similarly, in 8-array PSK, you can know that there are 8 phase changes, and in M-array, M phase changes. And coming to the bandwidth of QPSK, the general expression for bandwidth of PSK is 2FP by N, where N is the number of bits grouped per symbol. In QPSK, we know 2, N is 2. So that's why the bandwidth is 2FP by 2, which is equal to FP. So remember that the bandwidth of QPSK is half to that of bandwidth of BPSK, because we discussed in the earlier modules that bandwidth of BPSK is 2FP. So in terms of bandwidth, we can say that it is reduced to half compared to that of BPSK. That is the main advantage of QPSK. And we discussed that it has 4 phase changes. QPSK has 4 phase changes for 4 combinations of inputs, 0, 0, 0, 1, 1, 0 and 1, 1, because you are grouping 2 bits per symbol. So 2 bits, we have 4 combinations. And remember that here 4 phase carriers, 2 1-bit energy carriers. One is phi e of t and other is phi naught of t. Here you should remember that QPSK you can interpret as a 2 independent BPSK systems, one in the in phase and other in the quadrature phase. So for a binary digit 0, the voltage level is -1, and for the data 1, the voltage level is +1. And we already discussed that phi is the energy, x-axis represents the 1-bit energy carrier due to I channel. And similarly, 1-bit energy carrier due to Q channel be phi naught of t, which is represented with the y-axis. And also this is due to the odd sequence. That's why we have represented O here. And E represents the even sequence. Because you are going to split the input into first you are going to convert the binary data sequence into a bipolar signal having 2 levels +1 and plus or minus 1. So now this B of t is split into even sequence and odd sequence. We know for the even sequence we have taken the 1-bit energy carrier as phi u of t, that is root 2 ps cos 2 pi fct. So remember that this is in phase carrier. And in the Q channel, so you have 2 channels, one is I channel and Q channel. I channel represents in phase channel and Q channel represents the quadrature phase channel. So for the Q channel, the input is B naught, that is an odd sequence of B of t. And this is, and here you can see that the quadrature carrier is root 2 by ts sine 2 by fct. Now coming to the B of t, which is split into even sequence and odd sequence by a demultiplexer. If you see the I channel, B of t magnitude is raised by a factor of root 2 ps, root over ps into ts, which is multiplied by 1-bit energy carrier to produce the output of I channel as SE of t, S suffix E of t. And similarly, V naught of t in the Q channel is raised by a magnitude of root PSTS with the help of a level shifter and multiplied by the 1-bit quadrature carrier, 1-bit energy carrier, root 2 by ts sine 2 by fct. So sine represents the quadrature phase, which can be obtained by applying the in phase carrier to a Hilbert transform. So let S naught of t be the output of Q channel. Now the two sequences SC of t and S naught of t are added to produce the quadrature phase shift keying modulated signal. So this is the generation principle of QPSK. And now coming to the, let us see how P of t is split into even and odd sequences. This is our original sequence, 0, 1, 1, 0, 1, 0. And if you see B naught of t, in B naught of t, the odd sequence is a one which starts at odd numericals, that is 1, 3, 5, 7. And it remains the same till the next odd interval arrives. Similarly, BE of t occurs only at even intervals 2, 4, 6, 8. For example, if you see the odd sequence, here the amplitude of B of t is 0 at interval 1. So that's why same amplitude is continue. So we'll continue with the same amplitude till next odd sample arrives. So that is 3. So again at 3 you will observe the magnitude, that is 1. So one magnitude will continue for 3 and 4 intervals, and next we will check for 5. For 5 also you have magnitude as 1 only. So 1 will continue for 5 and 6 intervals. Again odd sequence will check at 7. So for 7 and 8 it remains same. And similarly even sequence will occur at even intervals, and for the odd intervals it remains the same amplitude as the earlier even sequence. So we have seen the generation block diagram. In level shifter for I channel and Q channel, we have seen the magnitude raised by root PSTS. So we can express SE of t as BU of t into, where BU of t is the even sequence. What is SE of t now? It is the output of in-phase channel or I channel. BU of t root PSTS into root over 2 by TS cos 2 by FCT. Now we know that this is quadrature carrier. You can say that 1 bit energy carrier in the in phase. Similarly, let us represent the output of Q phase channel as B naught of t root PSTS into root 2 by TS sin 2 by FCT. This is called as phi naught of t, that is root 2 by TS sin 2 by FCT. So total output is a sum of outputs due to the I channel and Q channel, that is SC of t and S naught of t. Just we have taken the expressions of SC of t and S naught of t, we substituted here, and we are going to replace in terms of symbol energy and 1 bit energy carriers. The same way what we did in the binary keying techniques, that is we discussed in the earlier modules. The BU of t just we multiplied with and divided with root TS, and we have taken that root TS inside the root to represent it as a symbol energy, where ES is PS into TS. And phi E of t can be, this can be taken as phi E of t, and phi naught of t we can take it as root 2 by TS sin 2 by FCT. So finally you obtain the output of QPSK as BU of t root ES phi E of t plus B naught of t root ES phi naught of t. With this, you can calculate the Euclidean distance. So Euclidean distance between any two successive symbols, that can be either S2, S1 or S3, S2 or S4, S3 or S1, S4. You can calculate any distance here between any two successive carriers. Due to orthogonal carriers, phi u of t and phi naught of t can be obtained by using the Pythagoras theorem. Then you will get a root es whole square plus root es whole square under root. So then it is a root over 2es. So you can write root es as root over 2 ps into ts. But here remember that in QPSK, because we have 2 bits per symbol, ts is equal to 2 dB. So we can write the Euclidean distance as root over 2ps into 2 TB, because ts is equal to 2 TB for QPSK. So finally you obtained it as 2 root EB. See, that is same as that of BPSK, because in BPSK also we obtained 2 root ES. So 2 root PS into TB, but in BPSK TS is equal to TB. So that's why you can observe that Euclidean distance for QPSK as well as BPSK both are same. That is, even though you are grouping 2 bits per symbol by using PSK in QPSK, probability of error performance is same for QPSK as well as BPSK. That is the main advantage of QPSK, so that the SNR also remains same for both the systems, even though you group the 2 bits per symbol. So bandwidth is also less for QPSK. So these are all the advantages of QPSK. Let us see the coherent detection of QPSK. You can see the block diagram. It is almost all similar to that of BPSK, which we learned in the earlier modules. And now the received QPSK signal, what we will do, first it will be collected by the receiving antenna, and it is applied to the 3 blocks to generate this in-phase carrier and quadrature phase carrier. First we will take the QPSK signal and raise the magnitude by power 4. In BPSK, here you will have square law device. But here, because you are grouping 2 bits per symbol and having 4 phase changes, we will take power 4. And next it is applied to the band pass filter with a bandwidth of 4 FC. In BPSK, you have 2 FC. And instead of frequency divided by 2 in BPSK, in QPSK, you will have frequency divided by 4. So that you can get cos 2 pi FCT as the in-phase carrier. And once it is applied to the Hilbert transform, you will get Q-phase carrier, that is quadrature carrier, that is sin 2 pi FCT. So this cos 2 pi FCT is multiplied with the upcoming QPSK signal, so that you will and applied to the integrator, which integrates the even interval, that is 2k TB to 2k plus 2 TB. This is an even integration. So then you will get BE of t into TB into root 2PS. Similarly, in the output of multiplier 2 will be the product of QPSK signal and quadrature carrier. So that is applied to the integrator, which integrates the odd intervals. So you will get B naught of t into TB into root 2PS. Now the two outputs are applied to the multiplexer to get the demodulated signal, which is same as a binary sequence transmitted at the QPSK transmitter. In the transmitter section, we have used a demultiplexer to split B of t into even and odd sequences. And at the receiver, you are using a multiplexer that will merge or transmit at a time the two signals, two sequences, that is due to even sequence and odd sequence to reconstruct the demodulated signal. Let us go through the analysis part. This phase lock, we already discussed this concept everywhere. Phase lock is due to frequency or phase synchronization and timing synchronization. And we know that timing synchronization is provided by bit synchronizer. Or here switching instance will match with the of receiver will match with that of transmitter. And frequency or phase synchronization is provided by the carrier, that is coherent carrier, which is provided by the 3 blocks. And in-phase carrier and the incoming PSK are applied to the correlator one, followed by low-pass filter to perform integration for even sequences. And similarly, QPSK and quadrature carrier are applied to the quadrature correlator, that is correlator 2, to perform integration. You are applying low-pass filter. And again, at the end, you will use a multiplexer to match the two sequences. So here QPSK, we know that this is the general form of QPSK. Now let us see the multiplier 1 output in correlator 1. So QPSK into cos omega CT. So we have taken QPSK signal and multiplied with cos. So here we have cos omega CT, and if it is multiplied by cos, you will get cos square omega CT, which can be written as 1 plus cos 2 omega CT by 2. And here second term will be sin omega CT into cos omega CT. So it will be sin 2 omega CT, which is a higher frequency component. And in the first term also, if you observe, cos 2 omega CT is a higher component. So our low pass filter does not allow these higher frequency components. It will allow only the sin 0 is 0. So the whole term, second term will be 0. So you will get only the output due to first term, that is BU of t root 2PS into by 2. So we can say that the output of upper sequence is BU of t, upper correlator is BU of t into root PS by 2. So if you allow this to the low pass filter, then and apply the limits from 2k TB to 2k plus 2 TB, you will get TB into root 2PS into BU of T, because and this is integration of, because BU of T and root PS by 2 is independent of integration, so you can take it outside. Then you will get 2k TB, just apply the limits. So for T, just apply the limits, 2k plus 2 into TB, that is 2k TB plus 2 TB minus 2k TB, the lower limit. Then here 2k 2b, 2k TB gets cancelled, you will get 2 TB, and already here you have 2 in the denominator inside the root. So you will get root 2 inside the root for numerator. So TB into root 2PS into BU of T. Low pass filter output from correlator 1 is L1, which is proportional to BU of T. Similarly, you can see that multiplier 2 output takes the product of QPSK signal and sine omega CT. Instead of cosine, you will have sine here in the correlator 2. Similarly, the low pass filter does not allow all the high frequencies, and you will get the output as P naught of T into root PS by 2. Let us see the integration for the odd intervals. For the odd intervals, you will get 2k TB plus TB minus 2k TB plus TB. So again, you will have similar expression, but in terms of odd sequence. TB into root 2PS into P naught of T. Now we will compare the outputs from correlator 1. Here what we will do, we will take the outputs of correlator 1 and that is in terms of even sequence, and correlator 2, that is in terms of odd sequence. Both are applied to the multiplexer. This will merge the two bit sequences without any disturbance to reconstruct the original sequence P of T. So this demultiplexer at the transmitter and multiplexer at the receiver will provide the timing synchronization. Synchronous carriers will provide the frequency synchronization, frequency or phase. Here coherent, because we are using the coherent detection, this will reduce the probability of error. So we can conclude that there are so many advantages from QPSK when compared to BPSK, as well as the existing earlier techniques. For QPSK, bandwidth is FP only, so that is one advantage, half to that of BPSK. Similarly, here we are grouping 2 bits per symbol. And another thing is because it has the same Euclidean distance, the probability of error of it also remains same as BPSK. So SNR is also good, and it also offers high power efficiency. So these are all the advantages of QPSK. And in QPSK, we don't have amplitude variations similar to BPSK. So it is a highly noise immune. These are all the advantages of QPSK. Again, the same drawback, somewhat the design is complex, and maintaining the synchronizations is also difficult. But once we maintain automatically, the SNR is good with less probability of error. So these are all the applications of QPSK. It's used in optical communications, biometric systems, contactless operations, RFIDs, Bluetooth, and along with the applications of BPSK, it is also used in GSM, similarly CD, code division, multiple access, long-term evaluation, wireless LAN. So multiple number of applications, even satellite and cable TV applications also, we can use this QPSK transmission technique. And these are all the applications. So in this module, we have learned the QPSK transmitter and receiver section. And in the next module, we can start continue with the MRA PSK. Thank you for listening.